acted as a barrier to this recording. Sorry, barrier to this flow of charge carriers. So this was the height of the barrier potential. Is it fine? It's getting blurred.
Yes, sir.
Just a minute. The light in the room is changing. The weather outside is, yeah. Now it's good. Okay. Acha, Adish, you just tell Priyam to rejoin. Okay. He just dropped off due to some technical problem. Tell him to rejoin.
All right, sir.
So today we will be seeing that how we can decrease this barrier so that we can uh, have a flow of current. Okay. So what we can do by applying necessary potential difference across the P and insides, we can have a good flow of carriers across the depletion region. Okay. I mean the P side, N side, between them, if I connect potential difference, which has to be such that there would be a good flow of charges across the depletion region, which was previously not possible. Then this thing would be called as forward biasing the PN junction. Got it? We have to apply such a potential difference across P and N such that there would be flow of carriers across the depletion region, and this thing is called doing forward biasing. So what we will do, this thing I won't be drawing in that much detail from now onwards. I mean, I'll just simply put a block like this. This is the P side, it is the N side, it's the junction. Fine. So what I will do, I will connect the positive terminal to the P side and negative terminal to the N side. Got it? What I am doing?
Yes, sir.
Now suppose the EMF of this battery is V. Okay. Not here, it's actually the external voltage applied, V. So what it will do, now see, the P side is getting positive charges and inside is getting negative charges. So now what will happen?
Flow of current, sir, from positive to negative.
Yeah, that is expected to happen. But why is it happening? Because see now, the majority carriers on the inside, which is the electrons would be attracted towards the positive terminal. That is, now see, if you give some external energy or voltage, whatever, from outside, then you can say that your charge carriers can penetrate the depletion region. Okay, on its own, it cannot do that. Similarly, the hole should be attracted towards the negative charges accumulated here. That is the negative terminal, and they will move this way. So we know that if holes are moving this way, then that is also the flow direction of flow of current. And if electrons are moving this way, then also the flow of current would be along this direction only. So as a result, what happens? Current is flowing from here to here. That is, it is coming from positive terminal to the negative terminal. Fine. So compared to the previous case when there was no external voltage applied, when it was in the open circuit condition, here we have a relatively very high flow of charges. Clear? And when I'm talking about these flows, these are mainly I'm talking about the flow of the majority carriers. And the minority carriers, see that they don't care much. They would be flowing like in the open circuit condition. That is, if the minority carrier is here, they will flow. And the direction of flow of minority carrier is opposite to that of the majority carrier. So if you have current in the forward direction in milliampere order, then you can expect the flow of the minority carrier charges constitute a very less current, like micrometer or microampere or nanoampere. So overall, what is happening? Let's see what happens to the potential. I mean barrier potential. What happens to its side? Previously, it was like this, isn't it? Previously, it was like this. This was VB. So what will happen due to the application of an external voltage VB? This thing will not see. It can't totally vanish. That is not possible, but it will get diminished. So what is the potential difference now? Sorry, what is the height of the barrier potential now? It has decreased by an amount V. Okay, it is now VB minus V. Is it clear?
The decrease, so
Which one?
mean that my minority current will affect the majority, so
See, majority current is flowing this way. That's the direction of majority current. Okay. Minority current is what? It will flow in the opposite direction. Why? Because here I have minority holes. These holes will go this way. They will get drifted. Once they reach the potential junction, they'll be attracted by the, even without application of this external voltage, we saw that there is flow of minority carrier, and that minority current is very small. Very small. If this is of the order of milliampere, this can be, depending on the transistor, material used, it can be as low as nanoampere or microampere. So if you want to subtract it, so what is your net current? Your net current is the order of milliampere minus nanoampere. Are you getting it?
yes, sir.
Nanoampere is what? 10 to the power minus 9. That means nano, and milli is 10 to the power minus 3. 10 to the power minus 3. So you can see this current is 10 to the power 1 million times smaller than this current. It's like subtracting 1 rupee from 1 billion rupee. Okay, that doesn't make much sense. So that current is not affecting this flow. Overall, what we can say, yeah, we are getting a current in the order of milliampere. Now that is good when it comes to application. That is this current is beneficial. I can use this for practical purpose. Clear? So this is what happens when you put forward bias. What you have to do, you have to give the P side positive potential, N side negative potential. As a result, what will happen? The depletion height of the barrier potential will be shrinked. It will decrease. And if you want to draw the diagram in terms of the barrier potential, sorry, depletion region, okay, then previously, if this was your depletion region previously, then now what will happen? It will become thinner. Okay, so the depletion region has become thinner. That is the wall that the, just think it this way, the majority carriers had to penetrate a wall. Now the wall has become thinner. So the probability to penetrate the wall is now more, isn't it?
No, it's like so they are it's
Previously it
easy for them.
was this thick. This was for open circuit. It was thick. But now when you are doing forward bias, see it has become thinner. That is if you want to visualize from the depletion region point of view. But I think this thing is more comprehensive. There was a potential barrier of height, this one. Now this potential barrier has decreased. Okay, are you getting it?
Yes, sir.
Is it clear, Aryanjali, Rudonil? Okay, fine. Now what if the reverse connection is done? I mean, is it always like that I will do the connection like this? What happens if I do the connection the other way around? That is, I have a PN junction. Hmm. Now what if I connect the other way around? I'm using the same battery, but I've changed the terminals. Got it?
No electrons are the majority carriers, no, sir.
No, no, no. That is the misconception many people have. See, who is the majority, who is the minority, that is fixed. N side will always have electron as majority carrier, P side will always have electron as minority carrier. That is fixed. This thing can't affect that. I got your, I mean, what you want to say understood, but the explanation is not fully correct. See what happens. Now this side is positive, this side is negative. The P side already has holes which are positively charged. So there is no way, no probability that very less or no probability that these holes will be going to the inside. Why? Because inside has already a positive terminal connected to it. So why would these things go? That is, the hole should be repelled. Similarly, the electrons from inside cannot come to the P side. Why? There is a negative terminal. So electrons should be repelled. Got it?
Yes, sir.
See, minority carrier, at the first place they are very less in number. Say majority carriers, they are say 10 to the power 23. Then minority carriers is only 10 to the power 2. Just compare. Just compare the relative density, relative abundance of majority carrier. So see, if you have the, if you have the majority carriers active, that is, if current flow is due to their motion, then whether minority carrier is flowing or not, that thing will not hamper at all the overall current flow. Okay. If this many particles are carriers are active, then activity of this thing becomes very negligible. Now what is happening? These many things are very less active. Now you have only minority carriers. That is, you have holes this way as minority, and you have electron this way as minority. Now what will happen? They will be drifted this way. Why? Because of this. Okay. Actually, it is not that this potential affects them. The reason is that the nature of the potential at the junction. That is, now what is happening now? Now what will happen? Since the majority carriers are now not having any ease to move down the depletion region, that is, it was previously this thing. Now what has happened is that even this depletion region has gotten now, sorry, this height has now gotten increased. Got it? And due to the increase of this barrier potential height, what happens? The majority carrier flow will be shunted. But see, for the minority carrier, doesn't matter whether it is positive or negative. If they reach the junction, they will just fall down. Same thing, the person escaping. It doesn't matter whether the walls of the no man's land has become taller or if that has become broader. Once he reaches there, he would be taken by the uh, forces on the other side. He has to reach there just. Are you getting my point?
Yes, sir.
Minority carriers, whether you are keeping it in open circuit, sorry, forward bias, reverse bias, whatever you are uh, giving it, this is voltage, this is the distance from the junction. The only requisition for them is to reach the junction, then it will fall down. I mean, here it doesn't fall down. In terms of potential, it is like they are being attracted by the potential on the other side. So keep this thing in mind. So what will happen here? We have something called, so this is called the reverse biasing. This is the reverse biased condition, or this is called reverse biasing. And the current in this case is called the reverse saturation current. The current which flows through the the PN junction in reverse biasing is called reverse saturation current. Now, can someone tell me what does the word saturation mean? I mean, reverse is okay. It is in reverse bias, that's why it's called reverse. Any idea why is it called saturation? Full. Yeah, you are coming closer. Yeah, with rest. Yeah, I think you want to say those things: saturated solution, unsaturated. Okay, what happens when we are full? Can we take anything else? Where once we are full,
No, sir.
so saturation, in a sense, it means we are its content satisfied. That is saturation in physics. When we say something is saturated, what we mean? We mean that something has become fixed or constant. Okay, we say now the graph is saturated at that point. So why is this saturation happening for this current? So this current is independent of the applied voltage V, right? Doesn't matter whether you are giving 5 5 volt, this is actually minus 5 volt in the opposite direction, or whether if you give 5 volt, 10 volt, doesn't matter. It is independent of the applied potential voltage, but it depends only on the temperature. Why on the temperature? Because temperature is the only reason why the magnetic carriers are getting the energy. Same thing is with the majority carriers as well. But what I said, if a magnetic carrier has gotten sufficient thermal energy to just reach the junction, then it would be carried easily to the other side. That's why it is called reverse saturation current. We'll even see in the graph when we'll do the experiment, the current in this region is more or less constant. Is it fine?
Yes, sir.
Okay. So now you all might have gotten confused that in forward bias there is current in one direction, and reverse bias I am telling that there is almost no contribution due to the majority carriers, but only due to minority carrier we are having a current. Then what is the point? I mean, we are getting current in both the biasing, forward and reverse biasing. Okay.
Excuse me,
So
sir.
yes,
So, like, is it like it has attained maximum current, sir? Like saturation current means? Is it like that?
kind of. But actually this thing is when we'll do the graph we'll see. Yes, yes. No, no, you can't even say maxima. See, when we say at a maximum current, like just remember the LCR graph. Hmm. So this is where it attains maxima, isn't it? So we can't say it is saturated there. What we mean by saturation, it may be something like this, that it was changing. This we can say, here it has become saturated. Okay. Or it can also be like this, maybe it is decreasing, it becomes saturated. Saturated always doesn't mean that it has to, increase and then become fixed. Okay. It is just a particular uh, point in the graph after which this thing happens. After
Okay,
a
sir.
particular point, if your graph becomes fixed, I mean constant, then we can say it is saturated. And you may say that, sir, then why are we not calling it is constant? If it is like this, right from the beginning it was independent of any parameter, we can call this one as constant. From the beginning it wasn't changing. But if it is like that, it is fluctuating, increasing, then it become this. Then we'll say it saturates here. Got it? That is the difference between constant and saturation. Being constant and being and getting saturated. Fine.
Yes, sir. Yes, sir.
Okay. So now, in a nutshell, what is happening? In forward bias, the current is of the order of this stands to tilde. This stands for the order. Current is of the order of milliampere. And in reverse bias, current is of the order of microampere if you are using a silicon semiconductor, and as low as nanoampere if you are using a germanium semiconductor. Okay, if you are using germanium, it is as low as nanoampere. Now the problem is that nanoammeters are not very common in all the labs. You have seen the ammeter thing, the white colored small box which has a hand that is sticking like a clock, which is
Yes, sir.
reflecting rather. So no problem, we can use a multimeter if possible. We can use that. So these currents are practically of no use. I mean, no one would be happy to use. At least we human beings, we won't be happy to apply these currents for our own task. This won't help. But milliampere is something which is beneficial. This is practically utilizable. So you must have a confusion that the reverse current is this way, forward current is that way. But a reverse current practically has no use. So this is what happens. So what we can say practically, for a PN junction, we say that when it is in forward bias, it conducts heavily. Why? Because the majority carrier, which are majority in number, they are flowing. So you can expect a huge amount of current to flow. And practically in reverse bias, we can say that no, actually it is actually no or negligible current flow. Got it? So we can say that in reverse bias, no current is flowing. Is it clear?
Yes, sir.
So
Yes,
if you
sir.
use the PN junction in forward bias, it will help you. It conducts current. In reverse bias, it is of no use. Don't be disheartened that why are we then using the reverse bias? Think it this way. Think of the water tap in your home. Okay. Uh, yeah. Now, if your home has those artificial intelligence tap when where you put the hand below the nozzle, water flows, then this won't count. If you have those old school taps, so you know that if you open it in one direction, which direction? If you're using the right hand, if you're opening it in the anti-clockwise direction, if you turn the anti-clockwise way, water will flow. And if you turn it the clockwise way, I'm using the right hand, then there won't be any flow of water, isn't it?
Yes, sir.
At least in our country. There are many countries I heard which are left-handed, where the things are in opposite direction. So now compare it this way. Had it been like if you rotated it clockwise, water is flowing this way. If you're rotating it anti-clockwise, water is flowing say in the opposite direction, or water is not flowing in this direction as expected. So that is not of any use, isn't it? That happens when there is some defect in the tap. Do you know what is inside the tap? What is here inside?
No, sir, but
Has
I'm guessing
anyone?
some kind of screw.
Yeah, screw is there definitely. There is something called a valve. A valve is a very, I mean, common name in different branches. It depends on the branch. Like in biology, also you will see some channels of flow of blood. They act as valve. Hmm. Artery or vein, just Google it. You will find it. So here, what happens? Valve is something which allows the flow in only one direction. So what is happening here? Once you're turning it the anti-clockwise way, this thing is opening. and once you're turning it the clockwise way, this thing is getting closed. So valve is what? Valve gives you only unidirectional flow. It is flow in one direction only. So can't we use a PN junction as a valve with this property? Can you use it as a valve?
Yes, sir, but only in forward bias.
Exactly. Because in reverse bias, no, in reverse bias also it will act as a valve. That means when we are applying some connection, this thing can be used as a valve. Okay. Now we don't use the word valve here. What we use instead, we use this function by a name called rectifier. Rectifier. We'll study it in great details in the next chapter. Okay, just wait, my network is not that good. Any idea what is a rectifier?
So
You had
like
all
it
these things in your school days.
rectifies
Yes?
signal, then allows
Yeah,
like half of the signal to
yes, it
go. So
rectifies.
like all
Yes,
how much
go
we
ahead.
require. So
So rectifier converts AC to DC, no? Half wave,
Right,
full wave rectifier.
right, half and full wave. Correct. So what is the idea? Idea is that I discussed this thing in my first class of CC3. That is nearly 1 year ago. Yeah, 1 year ago. When I was teaching you alternating current, the first class I said that there is a lot of misconception, confusion regarding DC current. AC current is good. It's okay. Like if you are talking about an AC current, suppose I, here if you're plotting a DC, it is usually given by capital letters. So AC is something which can have both directions. Okay, it is not so beautiful every time. It can also be treated as an AC, where it changes direction. It has two direction. Now DC, I said that DC doesn't always mean it is constant like this, but DC means that its direction is always same. See, direction means what? Negative and positive I am talking about. Got it? What I am talking about? So this continuous change in direction, this damages many electronic appliances and electrical appliances. Okay, so what we can do, if we can somehow, you know, apply this PN junction property of as a valve, what we can get current only in one direction. That is what we call rectification. Okay, that is what we mean by a rectifier. Fine.
so
That means you all can little bit, recall what you learned in school. Yeah, that's good. Good to know.
so is there any other use of like reverse bias current?
Yes, we will see that. See, now the only use of reverse bias current is that it is not allowing any flow of practical flow of current. Okay, that is its use in a sense. Got it? I mean, it is not giving you something useful. That is its use for the time being. Later on, we'll see what if we can use it in that direction. Okay, if we can use it. Are you getting my point?
Yes, sir.
For the time being, you think it that it is not giving you any useful current in the reverse direction. That is its use, because already you are getting current. By the way, the current in the forward bias is sometimes called forward current. Okay, don't get confused. It's not about only the direction. It's about the biasing. Okay, so now what is the current relationship? Current voltage relationship. That is important. So what is the current voltage relationship? This thing we will, in fact, it is the first practical that we would be doing. I don't know when things will be normalized. So let me give you the observation first, that is interesting. The equation I may give later on as well. So what we are plotting? We are plotting the current versus voltage graph. Now this graph is a bit different. On the positive side of the y-axis, you have to plot forward current. Okay, which would be in milliampere. I mean, these graduations will be for milliampere order. And on the positive side of the x-axis, you have to plot forward bias voltage, or it is sometimes called forward voltage, which will be obviously in volts. Understood how I will plot it?
Yes, sir.
On the negative side, no such issue. I mean, here I will plot the reverse voltage. That would also be in volts this way. This way it is the increasing negative. Now the thing is that here it may be like I may require voltage from 0 to say 30 volt, but here I may not require that much voltage. I may require voltage in fractions. So 0, 0.1, 0.2, 0.3 like that, but here I may require 0, 1, 2, then 4, then say 6, 8, 20 like that. And the very peculiar thing is that on the negative side of the x-axis I would be plotting reverse current. Now that's not the peculiarity alone. Now this should be in either milliampere if you're using silicon, sorry, microampere if you're using silicon, or it will be in nanoampere if you're using germanium semiconductor. Got it? So see, all the divisions are different. It's not like the normal graph that we draw. And if you don't draw this thing on a single graph, it won't be meaningful. So what is observed that if we increase the current in forward direction, that is we are applied forward bias, we are increasing slowly the voltage. Initially we will see there is no flow of current, not a very good flow of current. But after a particular point, we will see current rises, and then rapidly goes on rising in the forward direction. There is a particular voltage in the forward direction which we need to apply for an appreciable flow of current. Got it? Is it
Yes,
clear?
sir.
And this voltage is nearly 0.2 volt if you are using germanium, and this is nearly 0.7 volt if you are using silicon. Any idea why these values are here? Are you familiar with these values before? 0.7 volt, 0.2 volt? I think I discussed it someday.
Yes, sir.
What is this? What is this thing? Any idea?
This is
Aryanjali Rudrani? Yes?
required voltage, no, sir, to conduct.
Yeah. What is that thing? Why is it only 0.7 volt, not any other thing?
I don't know, sir.
No, no, you know, no, no. Didn't I tell you last day that the value of the barrier potential is nearly 0.2 volt for germanium and 0.7 volt for silicon? That is the height of the barrier potential. So you have to at least give this much of voltage to overcome that, isn't it?
Yes,
Yes,
sir.
sir.
And in the reverse direction, what happens? The current is like this. See, it is constant, isn't it? After this point, that is, we say it saturates. Okay, so got it?
So your screen is not visible.
Yeah, my screen. Let me share the screen. Just hold on. I'm using the second account. Just wait. Looking for a detailed graph. Hmm. Can you see my screen, everyone? I'm sharing it. Can you see my screen?
No,
Hello.
sir. Where is it, sir?
Now.
Oh, yes, sir.
So, yeah, this is what I was looking for. Let's see. Can I zoom it?
We can zoom from our side, sir.
There are many, Oh, right. You can zoom from there only. Oh, let me see. I think there is some animation here. Yeah. So you can see here, this is what I was talking about. Along this direction, they have plotted current in milliampere. See, the graduation is 5, 10, 15, 20, up to 40. Depends on the data that you would get. But in the reverse direction, see, in the bottom, they have plotted it of the order of microampere. Got it? Can you see this?
Yes, sir.
And see what I said. For germanium, it is nearly at least up to 0.3 volt. After that, you will get an appreciable amount of current flow. Now here they have plotted it like this. Practically, it's always like it's from 0 to suddenly current becomes increasing from this point. I mean, between 0 to zero point 0.3 volt, there is very slight increase in current. But now see here, there's a rapid increase in current. If you go from 0.3 to 0.4, say current will be increased by say 30 milliampere maybe. Huge increase in current suddenly. Okay, and for germanium, you have to give little bit more voltage to get this forward current. Now see for germanium, as I said, it is in nanoampere. So this current is constant. Okay, the width or the value of the current after this point is constant. It is saturated. But here also there is a particular point after which what we say we call the diode breaks down. See now here there's suddenly a huge flow of current. So our target would be to do the practical before this point. Beyond this point, if the transistor, if the diode, or we call this diode, we'll be calling it later. If the PN junction thing, if it goes beyond this point, it will be damaged and we can't repair it. Got it?
So can you tell me one more time, so this reverse characteristic, sir?
Reverse characteristic is it would be giving a constant current in the negative direction. You understood this thing, I think.
Like it's saturation, sir.
Saturation, yes. Saturation means what? After a particular point, it becomes fixed. More or less, it is constant. Okay. But here also, if beyond a particular reverse voltage, if you increase the voltage, there would be a huge flow of current in the reverse direction, and this current flow is uncontrollable. And whenever there is uncontrollable flow of something, damage is inevitable. Clear what I'm talking about?
Yes, sir.
So we have to take the reading, but before this point. I mean, we can take one data here so that the graph can be like from here to here. But usually we suppose if this current is say 1 microampere for saturation, this may be 100 microampere, and which we cannot measure accurately all the time. So practically what we would be doing, we would be taking the data for 2 3 regions in the reverse bias. So 2 3 data we'll see. If the current is constant, we just plot the graph. And practically it won't be always straight. It can be, I mean, there is a slight change. Okay, it will not always be parallel, but there is a slight change in the value in the reverse direction. Now, what people do, what students mistake, I think you remember, what's his name? Amir from maths honors. Remember Amir?
Yes, sir.
He did this practical in the, I mean, they were in the I think yearly system, not the semester system, huh? They had this, they used to call it pass course practical, not GE practical. I took their exam, and Amir could very beautifully explain this graph in the Viper. And now what, that is a good thing. The problem that I was talking about is Ganesh and Ayush, they made this mistake many times. That's not a very, I mean, huge blunder. It is very obvious. What students do, they make one graph for forward direction, for forward bias, and they make a separate graph for reverse bias. Don't do that. In the same graph, you have to plot both forward and reverse bias. Are you getting my point? Suppose you have plotted this thing in one graph, and this thing you have plotted separately in the other graph. That doesn't make any sense. Both the regions should be in the same graph. Only then will we be able to compare the, you know, relative values and nature of the graph in both the directions. Okay.
Okay, sir.
What I'm planning one day, just remind me in the next week. I will give you some data of this practical. You make the graph on your own and show me during the class. Just turn on your camera or send the picture on WhatsApp. Okay, this graph, this kind of graphs are not very common in our syllabus. That's why I'm a bit anxious. Fine. And
Yes,
by
sir.
the way, the good news is that next week you will be having your internals. We'll just give you the schedule in details. Got it?
Yes, sir. So even this presentation thing will
Yeah,
also
that
add
is
up, no,
this
sir?
week. That is this week.
So,
And next week we won't be having presentation. Yes, Rudra?
so internals as in like every subject, like all CC,
Yeah,
or
yeah,
like
yeah.
only one CC.
No. All CC. The thing is that what we are doing this time, or why we are doing this time, this thing is that